So one of the second order terms was this one, which we called Q2, which is negative VT1 VT1 plus T2 V0 rho EQ. Okay, what we want to do is we want to arrange it so that from left to right, the V's occur earlier and earlier in time. Right now they don't, right? This is in the middle, this is the latest, this is the earliest. So we look at this one, it's actually not so clear. If I move this over here, right, I'm still going to be T1 plus T2 V0 rho EQ, and then I'm back in the middle again. But if we look at Q2 star, we have a bit of help. So Q2 star is swapping the orders of it reverses the order of the operators. Remember, we only need to do one or the other. We don't need to do both. Right? And now we see this is great. When I convert this to the trace, the minus sign, we have V0, VT1, right? But I can move this over to here. So that means this is equal to VT1 plus T2, VT1, rho EQ, V0. And now I have them going in the correct order. So when I plug in the mu's and all that stuff, right, what's going to happen is I'm going to be operating with the mu from the right, So what's going to happen, I'm going to be operating with the mu from the right first, then I'm going to be operating with mu from the left, and ultimately the overall trace has mu on the left, right? So that you can actually say, okay, it looks like then I'm going to have a right operation and a left operation. So just to remind ourselves, this is the bra, this is the ket, sorry, this is the bra. So we're going to have a bra side interaction here and a ket side interaction here. Okay, so it turns out you can list all of these, and if you go through and work it out, you will end up just as an exercise I can leave for you, because I don't want to spend all my time on this stuff, but it's going to be equal to mu u naught T2 rho mu on the left, on the right, sorry, followed by rho on the left, mu on the left, because there's two of them, so I'm just keeping track of the order like this, and then u naught T2. Now you might ask, where did these get split up? Remember that the mu naughts, when you have T1 plus T2, that's really like saying I can evolve to T1, and then I can evolve from T1 to T2 again, right? So I can split the time evolution operator into those little pieces, and that's what gives you these little pieces here. So again, this is saying do the interaction from the right, then do the interaction from the left, right? And then you're going to evolve, and then you do the ultimate trace. Okay, so that gives you the way, for example, of just doing this whenever it looks really complicated. And it works for all of them. So you can do the third order ones where there's 4 terms, and you just move them around, 4 operators. All right, so what we're going to do now is we're going to work out a notation that allows us to list all the possible pathways. So far what we have here is a way of listing the interactions with the dipole operator. All right, and then we have a couple different pieces. We have another piece of information, which is not only do we have interaction with the dipole operator, we also have the field. Right? Our electric field, typically when we look at an experiment, we're going to pick a particular frequency to detect. So once we pick a particular frequency to detect or a particular direction, we will limit to a certain extent what signals that we will see, the signals that we can see. So plus or minus omega 1, plus or minus omega 2, plus or minus omega 3, and so on, for as many as we have. Same thing, the there's a one-to-one correspondence with the wave vector. And the reason why this is worth making very clear, in our field, in multidimensional optical spectroscopy, for a long time, people thought that the best way to do, for example, 2D spectroscopy was to use 3 different beams coming in from 3 different directions. This is just like the example I gave with the diffraction grating experiment. Remember, we had 2 beams, for example, like that, and then we had another beam coming from an angle, and then because the pump beams made a modulated index of refraction, we could get diffraction, the +1 order and the -1 order diffraction. Okay, now that's fine, and I do still think it's useful to think about nonlinear spectroscopy from the perspective of diffraction gratings. At the time when people were doing this, they thought that the greatest thing in the world was to have what was called a background-free signal. You put a detector here, and you only get anything on your detector at all when all 3 of these fields are present on your sample within the dephasing of the various transitions. Now, that's true, and you can get very high sensitivity from doing this. But then as we progressed and we wanted to measure electric fields, it turned out to be tricky. Remember, if you just stick a detector here and measure the intensity, you do not get the electric field, you get the intensity, which means that you can't, for example, do a Fourier transform with respect to some other degree of freedom and get something that gives you a field. You can get a frequency out, but it's possibly not the frequency you want. So when we moved towards doing 2-dimensional spectroscopy, which requires that you scan the time delay between these 2 pulses, the first 2, the signal will oscillate because you make a coherence, and then depending on when the second pulse gets there, your population will be either the ground state or the excited state, and it'll oscillate back and forth. When you detect the signal, that signal will oscillate back and forth. You do the Fourier transform of that with respect to T1, and you get a 2-dimensional spectrum. But you need to be able to measure the field to do that. Now, it turns out we do know how to measure fields. What you need to do at some point is you need to have another field that you interfere it with. Right, so you'd have the way to view this schematically is you have your signal, which is a field, and then you also have your sort of detection field. And the way people did it originally, they would put a time delay between these 2. When you make a time delay between 2 fields and then measure them in a spectrometer or do the Fourier transform, you'll have in the frequency domain, you'll have the envelope of your detection field, which is called a local oscillator from heterodyne detection in electronics. And then you have your signal. Generally speaking, your signal will be narrower in frequency than your local oscillator. So maybe your signal has some spectral components in it. And what you're going to see when you measure the intensity of this interference of the sum of these 2 is something that looks like this. That interference pattern you can analyze to get back to the field. I'm not going to talk about that here. Maybe I'll make another video that's not part of the course on this method. It's called spectral interferometry. So that sounded really good. It's like, all right, we have a background-free signal. All we have to do is bring in another field to do an interference detection, and we can get the field back out. But it turns out there's a bit of a problem with that, and that is you almost never know the absolute phase between these 2 things, which means when you do the Fourier transform and then the processing and the inverse Fourier transform, there's always an ambiguity of the phase of your signal. So when you take the real part or the imaginary part, which as you remember from the response functions is important, you might not have it properly aligned along the real or the imaginary part. You need to rotate the phase of your signal. It's like rotating one coordinate system to the other one. So that turns out to be a bit tedious. And what people realized, but they realized it in a kind of roundabout way, was that you don't actually need to do this experiment with 3 different beams in different directions. Right? All you need to do is have 3 fields. But if you make 2 of the beams the same, it looks just like a pump probe experiment. Right? But you still have a time delay between 2 excitation pulses, so you get excitation frequency dependence, sense of selectivity. But you just make K1 and K2 equal to each other. Right? And then what that does is it means that two of the Liouville space pathways that would normally be separated are collinear, and you measure them at the same time. So that's how I would say not the majority, but maybe the majority of people do 2D spectroscopy now. They have two beams. You only see two in the lab. That's a time delay, and you put a sample in the middle. And then there's no grading picture anymore in space because the two fields are exactly the same direction. The grading wave vector is 0. All right? So that means the signal turns on and off and on and off. It doesn't just shift where the fringes are in between. All right? And then what you do is you detect the signal. It goes in the same direction as your probe. And there's a well-defined phase relationship between your probe and your signal. So you don't even have to worry about this issue of converting the phases. All right, so this is doing it in a pump probe geometry. People first recognized this by using a pulse shaper to make this time delay. But then it was soon quickly realized that you could use any kind of interferometer to make a pulse pair like this. It doesn't have to be a fancy pulse shaper. In our lab in Lumos, in chemistry as well, we have setups that can do both of these methods. The one advantage of this is that you can control the intensity of this local oscillator field, whereas here you can't, not easily anyway. And so that means you're kind of stuck with the ratio of signal to probe for your interference detection. Whereas here you can make the probe local oscillator very, very strong, and you can amplify your signal quite a bit. That's true, and that's a limitation. But in practice, it only accounts for maybe, at best, an order of magnitude increase in sensitivity from here to here. The simplicity of alignment and the lack of need to worry about this phase problem makes the pump probe geometry quite attractive. Now, why am I going into all of this? I'm going into all of this because I think if people understood how to make the connections between the phase matching diagrams and the pathways at the beginning, we wouldn't have spent so much time in this struggling through how to get proper looking 2D spectra. We would have just done this from the beginning. And I'm not exactly sure, even though I was in this field at the time, I don't know why we didn't start with this. So when you're thinking about the point of teaching is to have the next generation come up with new ideas, don't make this mistake. Try to think about what your experiment measures from some kind of theoretical level first, and then maybe you can make the experiment faster and not have to worry about all the complications. We spent quite a number of years figuring out this issue of the phasing, and it turns out you really don't even need to worry about it all that much if you do the experiment like this. All right, so what we're going to do is we're going to recognize that we have pathways where we have the mu acting from the left and mu acting from the right. We need to enumerate them all. There's going to be basically, you can think of it as almost every possible way. Now you're going to have n interactions. So for third order, there'll be 3. The final one is the one that the signal is generated by from the having induced a time-dependent dipole moment, which then radiates. Okay, and what we're going to do is we're going to associate. We have to pick a particular signal that we're going to look at. That's true. So we're going to pick our signal, whatever it is, and when we look at the signs of each of the k's, if we see a positive k, we're going to make an arrow up to the right. And if we see a negative k, we're going to make an arrow up to the left. Okay? That's that simple. So what's an example of this? If my signal is a some frequency signal, so it might be k1 plus k2, this corresponds to an arrow up to the right and an arrow up to the right. If instead my signal was just linear, then I might have k1. Whoops, I don't know why I did it in a different color, but got carried away. Right, and that's an arrow up to the right. Now you might say, what about minus k1? Remember, we always have the negative of everything. Sure. So you can have ks is equal to minus k1 minus k2. It would just go in a different direction. And we would have this. And same thing with the linear case. All right, that's fine. What you're going to see is that we typically pick the one where the final signal has the mu operating from the left, and that's going to limit which of these we actually have. Okay, so you can do this also for higher order ones. So you might have a signal be K1 plus K2 plus K3, kind of like the sum frequency generation for third order. You might have it be where there's a minus sign somewhere. So maybe minus K1 plus K2 plus K3, for example. That'll be like this, and like this. Now you might say, what are these arrows for? Well, the arrows are for charting the density matrix. All right, so what we're going to do is we're going to write down the density matrix for the case of the linear ones. Now, how many interactions do we have? We have two interactions. We have the input field and we have the output for induction decay. So the way this diagram works is you have your density matrix represented as two elements, and you put a line every time there's an interaction between the field and the matter, and then you add your arrow onto this. Okay, so one way to do it would be to take this arrow here and put it like that. And remember, when the mu acted from the left, we went up on the ket side of the density operator. Right? And then what happens is the system evolves without the field. And the density operator evolves because you have u naught rho, u naught dagger, which is the way that you evolve rho in forward in time. Okay, so what's going to happen is the system's going to evolve during this time under the influence of the Hamiltonian in the absence of the field. And then there will be another instant when the signal emits. Now, we don't know when this is for this case. It's going to emit the whole time. But we can put it in anyway because perturbation theory, right, gives you the sum of after how you add up over all these times. Now, which way is the signal going to go? The signal is going to go out and it's going to operate from the left. So the convention, generally speaking, is that we consider our signals where the final mu, the act of computing the trace, is represented by operating outwards to the left. All right, so that would correspond to this pathway would correspond to this signal. Since K1 is equal to Ks, that means that the signal goes in the same direction as your input field. That's exactly what happens in linear absorption. You have one time delay, t, right? And the system evolves according to the coherence that you make. So let's say we have 0, 0 in the ground state, and I go to an excited state, A. Then this is going to be a signal that's like e to the minus I omega A0 t. Right? That's the Green's function for evolving. Now, could it decay? Absolutely. So I could have minus like gamma t. Omega, yeah. So I could have it multiplied by a decaying piece. That would be a way of including damping into the coherence. So that would mean that our coherence went something like this. We do the Fourier transform of the whole signal, we'll get an absorption spectrum. That looks like that. That's time and that's frequency. And the final mu puts us back to the ground state. And the rule is whenever you see the arrow pointing towards a diagram, you will make a transition upward on that side of the density operator, whichever it is. And when the arrow points away from the diagram, you make a transition downward. And that's it. Once you've done this, you can actually list every single pathway that there is for a given nonlinear experiment, provided you've chosen a particular signal direction to look. Okay, so let's look at some examples of that. Now, just to make sure it's clear, I can do this other case here. So now, can it go down? So you could ask yourself that question, can it go down? And so for our usual starting position, right, where we're in the ground state, if we're thinking about transitions of high energy, or high compared to KT, then there's no way to go down from 0. 0 is the minimum. So that means the only pathway available for this one is to come up on the right-hand side, which is exactly what we calculated in our example before. But because we've gone up, our emission has to be outwards this way, because there's no way to go outwards on the left. We're already at 0 here. So it has to be this. So these two diagrams are complex conjugates of each other. We do not need to separate them. And this is exactly what we found when we did it by hand, right? We found J and J star were complex conjugates of each other. So this corresponds to J, this corresponds to J star. And you only need to worry about 1/2 of those pairs. And it works like this for all the nonlinear response functions, no matter what order. There's always a pair. You only need to worry about one of the two pairs, whichever one's easier to understand, or from our convention, whichever one leads to signal emission, or the final trace acting on the left, going away. All right, so now we can do something like a sum frequency pathway. Let's take Ks, this one here. So K1 plus K2, I'll stick to my thing, my color coding. Now, how many interactions are there? There's 2 with the fields that we supply, and then there's 1 final trace. So we'll put 3 rungs on this ladder. Again, we start in the ground state. And we look, okay, so we have 2 arrows. We know the first one has to go up on the left because there's no way for it to go away on the right-hand side. It's already at the ground state. It's impossible to go down lower than the ground state. So this is going to bring us up to some excited state, which we'll call A again. I realize that A and 0 look very similar, but at least I'm talking. All right, so now what's the next thing that we can do? The second field could be on the left. Now, the thing I think I probably forgot to say is that these arrows' directions are fixed. The side of the density operator they act on are not. When you work through all of the commutators, you will find you get all the combinations. So the rule is you take the arrow, you allow it to slide around on your diagram, but you don't allow it to change its direction. So that means it could go on this side or it could go on that side, as long as it's pointing in the same direction. Now, can you go down from 0? No, you can't. So the only other signal that there is here, or only other pathway that could contribute is this one. So that means we need to go up again. Remember we proved that you can't have a nonlinear second-order signal from a 2-level system. There's no way for a 2-level system to go up higher. This would not exist. This would not work. Right? So we have to go to another level, B. All right? Then the final signal, again, is going to go out on the left and lead us back down. Now, where does it lead us back down to? It could lead us back down to A or 0. So I don't know yet. So this is the point. We have to do like sort of choose your own adventure. We get to this point, we either go back to A or we go back to 0. So it could be either one, so let's put it back to 0 for now. And now is when we have to start thinking about things that involve the molecule. Maybe the transition from B to 0 is forbidden. Right? Maybe this is a harmonic, something like a harmonic oscillator or an anharmonic oscillator. If it's an anharmonic oscillator, then what's going to happen is we're going to have 3 levels that we're considering. Right? We have 0, A, and B. The first field interaction made a coherence between 0 and A, so it kind of put us up into A. Now you see it's hard to make these kind of diagrams work because this is about the density operator and this looks like just energy levels. There are some tricks that you can do for making different diagrams like this. But we're talking about this close enough so it should make sense. We make a coherence between 0 and A. Then our field interacts to go from A to B. And then our coherence that we have is B0. So we could either end up back down here or we could end up back down here. Right? So that's what the final interaction will be. Now here's the trick. If we end up on A, what does that make our final density matrix? If we end up on A, that makes our final density matrix be rho A0. What's the trace of a matrix that has only an element on the off diagonal? It's 0. This term is exactly 0 because the dipole moment expectation value is 0. So here's another trick. You make your pathways and then you make sure that the final density matrix steps that you have is a population. meaning these two elements have to be the same. They don't have to be the ground state, but they have to be the same. Because if it's not the ground state, it'll be something else. Then when you trace it, you get some non-zero element. All right, so that's sort of the last piece of how to work with these diagrams. All these diagrams are called double-sided Feynman diagrams. The first invocation of these that I'm aware of in sort of systematic was due to someone named Bourdet from France. But you can actually find papers where people use these to understand nonlinear optics, borrowing on the ideas from sort of regular physics, regular electrodynamics, which is using diagrams to indicate how particles interact. Again, because of a series of perturbation theory that they're summing. Okay, so here's an example of some frequency generation. The important thing is to note which are the coherences. Here's a coherence, and the coherence is omega A0. But then there's a second coherence, omega B0. All right, so this involves two coherences. The coherence that's at one frequency and the coherence at the other. How is most commonly some frequency done? Most commonly, I would say, especially in our department, it's done where the first interaction is in the infrared and the second interaction involves a visible field. Right, so then the way that level diagram would look like, you have a vibrational transition, say a carbonyl stretch or a CH stretch, and then you make a coherence with the first infrared field that you apply. So this would be like 0 and A. And then usually the way many people do this is they have an electronic, they have a visible pulse or a visible field, which takes this coherence and creates a kind of, let's say, transient coherence, or a coherence that only exists while the field is on. Officially, you could say within the electronic dephasing time. The electronic dephasing time is usually very, very short. All right, and so then what you do is you make a coherence between a state that doesn't really exist, unfortunately sometimes called a virtual level. And then the ultimate signal that you detect is this one, the B0 energy. So what this looks like in the lab, it looks like you had a visible field that got shifted to higher frequency. Right? That's called an anti-Stokes shift. And the idea is that you can measure this, and it'll go in a particular direction because it's going to be the sum of the infrared and the visible fields, primarily the visible field direction because of the much longer wave vector of the visible. And then you detect it in a spectrometer or however you detect it, and you can measure that as a function of, for example, the tuning of this infrared field. And as you get towards a resonance, the signal will get huge, and as you go away from the resonance in the infrared, the signal will go away. And it won't depend much on the actual visible thing. But notice that this is an infrared transition. This is a dipole allowed infrared transition, which makes a coherence between two vibrational states. That is something that's called basically a Raman coherence. And so the final step that you get is actually a kind of Raman scattering from a coherence. And so this is, if this is dipole allowed, this is, let's call it Raman allowed. Which just means that the change in the polarizability has to be non-equals to 0. So in some frequency spectroscopy, when you do it with infrared and Raman, infrared and visible, it is selective to modes that have both infrared activity and Raman activity. So if there's small molecules, that might limit what molecules you can use. In bigger molecules, the symmetry is much lower. And so that it's very common for modes to have both Raman and IR activity. And I should say, of course, this is some frequency spectroscopy. It's second order. It requires that the system have a broken symmetry of inversion. And so the most common use for this is at some kind of interface. For example, like a solid liquid interface or a liquid air interface or whatever. So you need some kind of interface. And then the measurement that you do is sensitive to the molecules that are literally at the interface. It's remarkably sensitive in that way. The signals themselves are not huge, but the interface selectivity is probably the biggest selling point of doing surface sum frequency generation spectroscopy. Now, as an analytical technique, people tend to like just scan the energy here and then measure the intensity of a light that's coming out. That'll tell them the frequencies of the IR transitions at the interface. Unfortunately, it's not a very good way to measure the line shape. There's all kinds of artifacts that happen when you measure the intensity of SHG signals, or SFG signals. So I would not recommend anyone does that. Instead, you should do heterodyne detection to measure the SFG signal. That's much harder. You need to have another field that reflects and becomes the local oscillator to do that. There are several groups that have figured this out. And then in fact, you can do even more creative things than that. You can, once you've measured how to do the second harmonic or some frequency generation with heterodyne detection, you can bring in another field and excite the molecules of the sample, either with a photochemical process or just vibrationally excite them and watch. As a function of time between the vibrational excitation and the SFG probe, you can look at the vibrational dynamics at the interface, confounded by all the stuff that's happening in the bulk. And this is really one of the frontiers of ultrafast spectroscopy right now, is to study dynamics at interfaces. Most recently, there's a remarkable paper by Tahara in Nature Chemistry that just came out a couple weeks ago. I really love it. They looked at phenol photochemistry. Phenol is this molecule here. And if you excite it in the ultraviolet, you can actually cause a homolytic cleavage of this OH stretch. And they use this to monitor, they used second harmonic or some frequency spectroscopy, at the interface to look at the photochemistry of phenol at the interface. And they found that the dynamics is much, much, much different from what it is in bulk. Pretty incredible work there. I think that was from this year, 2021. So if you're interested in what is the absolute cutting edge of interfacial multidimensional or ultrafast spectroscopy, I would say that's pretty much ranks pretty close to the top right now. All right, so the next thing I'll do is walk you through the third order pathways, and then you'll be able to do it all by yourself because, as you see, the recipe is quite straightforward.